Good afternoon to everyone. I know it's kind of after lunch, so we'll try to make your time. We are going to talk about carrier use cases with OpenDaylight. My name is Ariel. I'm a CTO from ConteXtream, which now it's an HP company. We've just been acquired together with me.
Gal, I'm engineering director at ConteXtream.
So as for the agenda, it's actually my first time, so I'll try to be on time and not diverted. And we have a few use cases on a large carrier scale deployment. I will at first introduce them. After that, we just show an OpenDaylight carrier SDN architecture, which is our architecture. Our product is based on OpenDaylight. And we will explain what it takes to make an ODL carrier grade. Okay? So that's kind of a key part in our demonstration. Use cases in details after that, we will cover a little bit of those. Subscriber-aware service chaining, our key advantages in the industry is fine grain, very, very granular. We work on every subscriber, put his exact needs into the systems and configuring open flow rules accordingly for each subscriber, its own chain, and based on his requirement. After that, we will show a little bit something that's a bit more sophisticated, where we took OpenDaylight based platform and we make it the data path of a virtual EPC. So a lot of carriers talked about VNFs and moving the component from a physical component to a virtualized component. We took that steps, but we took another steps further, is translating the data path of EPC, which is kind of a not trivial data path. We move it to an open flow switch that actually performs the EPC. And the last use case that we'll demonstrate, that we'll talk about it, is Sdn Vpn based on ODL, all kinds of VPN use case and virtual CPEs use case that we are working on. And at the end, we'll try to do some kind of a scale demonstration where we show a system of 40 gig download, 10 gig uploads, 1 million subscribers, and 1,000 rules per second, serving a GI LAN use case with a fine grain service function chaining. So I'll start with describing some of the carrier SDN fabric that we're doing. So we split it to multiple categories based on voice, consumer, and enterprise. And we do from customers categories, whether it's cable, fixed, and mobile. So we identified six use cases that we started to work on. And we actually in a very progress stage in each one of them. So the first two use cases is voice related. Some of them we do have already in productions in a large carrier in the US. So we're doing a virtual IMS and a virtual SBC, where we take the IMS and virtualize that, make it a global load balancings between IMS cores. Same thing goes for SBC, session border controller. So you can virtualize multiple of them for NNI links. So that's kind of two use cases. In the consumer data, we're doing subscriber-aware service function chaining. That's for GI LAN. GI LAN is the endpoints of the EPC, the LTE environments, the 4G environments that you know. After that, you need all kinds of services. Most probably, most of you are getting those services, even if you're aware or not. So the ability to have all kinds of services introduced, that's kind of a use case that we do. the next use case is enabling EPC that I talked a little bit before. And the last two use cases are virtual CPEs and an Sdn VPN that they're somehow related, okay? So we'll demonstrate, I'll show what's in there. So I just very quickly go over these because I will have later on details. So each one, if I get it, sorry. I have the mouse. No, not this side. Okay, so this is the virtual CPE, virtual EPC use case where the data path component is actually being on an OpenFlow switch, and you have the control component, which are the regular EPC, but now they translate and move to, with the ODL controller, it moves to the context net and pushes to the OpenFlow switches. So that's on the left side. Okay. On the GI LAN, so that's service function chaining, subscriber aware, fine grain. I'll cover it later. Wi-Fi, SFC, same thing, very, very similar. And the two voice use cases, SBC load balancings and IMS load balancings, all subscriber goes to a context switch and goes to a different IMS core. Now, on the business services, so you have some branch office, you have headquarter offices, and the virtual CPEs, the CPE is kind of a DOM, aggregates into the actual CPEs, just aggregate into the center, and over here it gets to an OpenFlow switch, and all the other components are virtualized inside, whether it's on the branch, whether in the central, very, very similar, and aggregates into a virtualized environment. I'll get, good question. Just give me 2 slides, I'll get to that. And business services, I'll cover it later. Let's go to your question. I just wanted to show you just what are we talking about before I drill into the architecture. So we are connecting network equipments. We are connecting a virtualized components. They are residing, whether that's in the home or in the data centers, on the aggregation points, whatever they are, okay? And they are all connected in multiple locations. And between them, there's kind of a network, whatever, layer 2, layer 3 network. We treat it as an underlay network between them. In each location, we put an OpenFlow switch, okay, which is a context switch. And together with that, we put a context net controller, okay? The controller is an SDN controller based on OpenDaylight, which communicates with the switch, okay? Now, the switch is an OpenFlow switch that can be a mix and match of software OpenFlow switch and a hardware OpenFlow switch, or just software or just hardware, depending on the use case, okay? But it's just an OpenFlow switch that the controller knows how to configure it in a set of OpenFlow tables. I'll explain later which kind of tables we have and how that gets together. Now, the controller needs to be a federated controller because it's not the same location all the time. I cannot guarantee for you clustering. It can be different locations, one in the East Coast, one in the West Coast, or it can be unreliable connection between them. So the controller should be as close as possible to the controllee, but I cannot guarantee that between controller we'll have a good network. That's why we federate the controller between them. The communication between the controller, between the multiple location on the data path, we create an overlay network, which create overlay tunnel, whether that's VXLAN or whatever other NVGRE or whatever other mechanism of layering protocols, we actually don't care. That's kind of up to the switch to implement those layering. We prefer to work with the switch in a hybrid mode, where the switch takes care of the underlay. On the communication between the controller happening through the mapping service, okay? A controller talks to the mapping service. We have the list mapping service that component we contribute to OpenDaylight is part of the open source, where we communicate with the mapping service. And we use behind the mapping service some DHT database that acts as the mapping service. And it's globally federated, globally distributed, and multiple copies, highly available. So that takes care of the connection between the locations. And the controller talks to the mapping service, depending on the deployment type, whether the mapping service is local to the controller or just an entity of the mapping service local to controller, or it can be that the mapping service is remote in case of the controller needs to reside in a CPE device. Okay? So we have those use cases also. But in regular use cases, they are tied in. There is entity of the mapping service local to the controller, and we call it a ConteXtNet node. That's all combination of map, control, and switch is a ConteXtNet node, and you can have multiple ConteXtNet nodes communicating between each others and through passing through the underlay. As exposed from the mapping service to the northbound, we have a ConteXtNet broker that exposes the knowledge of the mapping service. Of course, we have also a management, which is communicating with the ConteXtNet nodes and exposing the management things, how everything looks like. And we have context view, which is all kinds of graphs, logs, ability to have logging, history, and all kinds of performance related. Now, the broker communicated whether that orchestration, OpenStack, LDAP service, AAA service, PCRF, all of that, we have a broker that communicating with those. Now, we have the ConteXtNet node, which actually is a mapping controller and an OpenFlow switch, okay? Now, we took the OpenFlow switch and put a set of OpenFlow tables. Some tables, we call them a subscriber or application switch, okay? We are subscriber aware, fine grain, a lot of subscriber rules, so that tables are very big, okay? To connect between one location to another, we're using a tunnel switch, okay? It's also a set of OpenFlow tables, no special switch, nothing. It's a set of OpenFlow tables, and that tells us how to get from one location to another location using the underlay, okay? So the subscriber switch is more about the overlay, and the tunnel switch is more about taking the underlay, okay? Now, it needs to be in a modular topology, okay? It is sometimes is very small in just one location, small form factor, and sometimes it's like a huge PGW that right now serving 2 million subscribers, okay? So all kinds of other use cases. And we need to optimize between hardware and software. So sometimes subscriber switch and tunnel switch are together on the same OpenFlow switch, and sometimes they are separated, okay? And we need to get into existing infrastructure, okay? So sometimes we can control the vSwitch in the hypervisor. Sometimes we are not allowed to, okay? If it gets to some public cloud or some other vendors actually doing the vSwitch, and we are not allowed to touch his tables, so we can reside on a VM, okay? And we are, for that, with just a default gateway of the VNFs, and that's how the traffic gets to us. And the actual Neutron plugin has not aware that he's been part of the service chaining, and we are doing the actual service selection of the service chaining. Now, that's why we define a few deployment use case, whether the tunnel switch is on the top of rack, and the subscriber switch can be in a VM or bare metal, where you utilize the SRIOVs and the PCI pass-throughs to get 160 gig of traffic in a single server, okay? And we utilize the top of rack to do the tunnel switching, and it can be like 3 terabytes on the top of rack, so that's kind of unlimited. Or it can be a switching in the hypervisor in case that we allow to do that, or a switching pool that you can spread your VMs in the rack, and or whether splitting a VM in every one of the servers in the pool, or whether that's in the top of rack once we have a top of rack that's capable for a lot of open-flow rules. I'm talking about millions of rules. Our subscriber switch can get to 100 million rules. And once you need 100 million rules, you need 100,000 rules per second. Because you have a lot of rules, you need to have a lot of updates. Okay? So that future of hardware tunnel switch and subscriber switch will come, but it's just a matter of time. So how it's being laid out, so in every place you have a context set node, okay? And between the different locations, you have an overlay tunneling between them and an underlay that connect them. And you have a different VMs on the outer lay that we're doing all kinds of service function chaining between them, or VPN, or all kinds of other use cases. The architecture, they remain the same. Our main focus is fine-grained and one single architecture for all use cases. That's kind of the things that we want to push further into the industry. Yes?
I have a question about deployment architectures. You talked about 100 million and 200 million flows being managed and throughput scale at that level. Across all these deployment options, would you mind sharing your viewpoint that how does your capacity and scale impact from bare metal to virtual machine implementations and so on and so forth? If you would like to talk about it.
Sure, I would love to. Once I go to every use case, I will explain exactly what's the special about that use case. And we have a demonstration, if we'll get to that, of 1 million subscribers and like, I don't know, we have 12 million.
Yeah, we'll see the ability to upscale, how we can add more switches and upscale the solution and still be resilient and handle the scale.
And of course, we are talking about carrier grade. Everything have to be highly available. So everything you have to write twice to different redundant switches and redundant controllers. So whenever anything fails, you have to continue to work. Now, just an example of one of the use cases that we do in subscriber OS service function chaining, just to give you a visibility how data path works between subscriber switch and a tunnel switch. So we have in every location context set node. We have the controller that talks to the mapping service, and the mapping service is on top of that, having the knowledge about each subscriber's where it is, each VNF where it is, what is the status, and the list is location identity separation protocol. We ask the mapping, what's the location, what's the identity, and what's the status, and we get that from the mapping service. Now, when the data path actually is being configured into the OpenFlow switches, so when a traffic comes in from a service function chaining from one VM to another, okay, and we say that we are subscriber aware, meaning that the traffic goes from a single VMs, it goes to usually a VM is a VNF. What is sent to is based on his next top router or his default MAC address or whatever you configure that VNF to be sending traffic to, okay? Even in a use case that we are not part of Neutron at all, always the VNF has a default destination. He will get into the subscriber switch. The subscriber switch will understand, okay, what was my previous VNF, okay, meaning like the source MAC address of the packet, and then it will look who is the subscriber. So depending on the direction of that interface, whether that's up to the internet or towards the subscribers, you look on the source IP or destination IP to identify the subscribers. And then you have a rule that hits the rule, whether that's coming from this VNF, this subscriber, what will be his next service, okay? Or what will be the next filtering that needs to have what, based on his application or something else, to hit what will be the next VNF. And there will be a rule over there that's saying, like, for this subscriber, the next VNF in line will be the next, this one, okay? So now that rule says, okay, go to the next table and have some kind of a cookie, okay? Or it can be a MAC address if that's the tunnel switch is not in the same OpenFlow switch. And then it goes to the OpenFlow tables, which belongs to the tunnel switch. And the tunnel switch will just forward encapsulate it based on the exact topology where the location of the destination VNF. And it goes to the other side's VNF, the tunnel switch get the packet, and just send it to the next VNF in line, whether that's physical VNF or logical VNF. So if you compare it with, it's really matched to also including SFC proxy, if you're aware about what SFC and shims and all about. Okay, so that allows you to have ability to have in network also VNFs that are not SFC aware.
Do you use one specific encapsulation or is it multiple?
We support multiple encapsulation. We leave it to the capabilities of the switch. Okay, we mainly focusing on trying to work with hybrid mode switches so that they will take care. We configure the tunnel, of course, but if they can use just an MPLS, we are fine with that. We prefer VXLAN, but now, what it takes to make a carrier grade ODL, okay? And a carrier grade is a lot about high availability, okay? A carrier cannot allow himself for service to fail, okay? When in a data centers, okay, just you have a single top of rack, and if a top of rack fails, that's fine, okay? Usually, the Google and the Amazon cover that in the application level and make sure that they have the redundancy in the applications, enough compute, other compute, take care of that. In a carrier, a rack can have a lot of subscribers on it, okay? Like few millions of subscribers in that rack being served. And he cannot allow himself that a single component will fail and he will have a service outage. So for that, everything needs to be highly available, fully redundant. So if we have multiple ConteXtNet nodes between them, actually in every one of them, we created N+1 redundancy between the controller nodes. So in a single node, we can have multiple controller and multiple maps, and all of them act as an N+1 redundancy, okay? So they are sharing the load between them, and if one of them fails, the others continue to work, okay? We will actually show that in the demonstration that we fail one of the controller, and you will see everything continue to work as usual. In every ConteXtNet node, there is a leader, okay? The leader is just responsible for defining the segmentation of the load, okay? Who gets which portion of the load. Actually, what we distinguish between scale task and non-scale task, okay? Non-scale task, configuring a VNF, or configuring an underlay, we have no problem that a single controller do that, okay? It's non-scale. A scale task is like handling subscribers. That can be in a rate of 1,000 per second or tens of thousands per second. That needs to be load shared between multiple controllers. So for that, the leader only decides about the split, and we segment the world of subscribers to some kind of a hash, and then each controller takes his own portion, okay? And controller obviously is in the same node, configure the same switches, okay, at the same time. So since there is no conflict between the segmentation, so there is no conflict inside the table. So a scale table is all the time configured by multiple controllers. Each one is on his own space. And that's how we get to throughput. So you ask about how we get to throughput. That's kind of the tricks that we do. And they also backed one each other's. So of course, the external interfaces is also redundant. And you have multiple underlays, okay? So it's not enough to have a single underlay between each location. You always have duplicate underlays that needs to be taken care of. And of course, once you get into the VNF, the same VNF has multiple access to it. So all of that, every component can fail. Control, data path, VNFs, switch, every component can fail, and everything needs to continue to work. Now, as for scalability, fine grain has its own advantages, but has its own requirements, okay? So a fine grain meaning that you configured a lot of rules. A lot of rules, you need capabilities, high capabilities. So the numbers that we are at is like 500 context node, multiple controllers, VMs, so controller running in a VM, in a context node, so you have multiple VM. But it's not enough. In each VM, you need multiple JVM, okay? OpenDaylight run in Java. Java has garbage collection. Garbage collection has limitation on the memory, okay? When you get a full GC, most of you knows that the JVM stops, okay? And that's very risky. In order to do that, you need to have multiple JVMs in a single VM, okay? Each one with a smaller footprint. And once you have a lot of JVMs, then you have the less potential of full GC, or that full GC will be shorter, okay? And so an assignment of VNF to OpenFlow switch, distribution highly available. So just the numbers that we are in a context node, we have up to 8 VMs, 64 JVMs, 1,000 OpenFlow switches, up to, depending on the use case, so 10K VNFs, and 10 million subscribers, okay? In each node, and you can have 500 of those. So the scalability is very, very high, depending on the use case. I said that this is like the other side of the use case where you have a huge ContextNet node, but sometimes there is a different use case that the same thing needs to go to in a CPE, okay? Which needs to be cost like $200 CPE, okay? So just different use cases, same architecture. Just a bit about external interface. I won't take too much time of that. So all kinds of external interfaces, orchestration, AAA. So working with carriers, a lot of transaction subscriber awareness coming from the AAA, whether that's PCRF, GX interfaces, and the radius interfaces. talking with application security, quality of service, OSS billings, all of that needs to be taken care of. Underlay, whether that all kinds of encapsulation, management, of course, VNF API overlay. I just skip that. A bit about the use cases. So I will drill into the detail where I think it's interesting. If you have questions, I can answer them. So on the GI use case, just service chaining, all of that was bump on the wire. Each VNF was scaled to the top and to the so scaled to the peak of in the next 5 years. And also, it was a long time to deploy each one of them. Once you put a ContentNet switch based on the subscribers, we can service chain that functions. And we demonstrate how you can take a VM, a VNF from the internet, download it, put it on a VM, and just select 1 or 2 subscribers to pass through that. So it's just a matter of few minutes of adding that to the systems instead of 18 months of testings and without risking your environment. We actually did that in one of the customers during a SIP call, during a Skype call with the customer, okay, while he's on his laptop, and we introduced another VNF in line, okay? And I told them, okay, so test it's working. Wait, I know it's working because we continue to talk, okay? So that's kind of how it's easy to introduce new VNF into that system. Now, the carrier challenge in that, okay? So it's millions of subscribers in every location, okay? It varies depending on the customers, but it's in every aggregation point. It's between 1 million to 10 million subscribers, and they can have multiple aggregation points, and VNFs can be in multiple locations. The changes. Tens of thousands of changes, subscriber registration, in and out. It's your mobile phone. Sometimes it works, sometimes it doesn't. It's connect, disconnect. Everybody noticed that. For the carrier, it's another attach, detached that translates to updating all these paths. It needs to be in multi-data centers. Not all the services are available on the same data center. Sometimes you exceeded the load in a single data center. You have to load share between other data centers. Okay? So it needs to be highly available and scalable. The redundancy requirements, as I talked before, very demanding. We'll demonstrate that. N+1 hot backup, instead of today, they are at 1+1 on everything and on a 10% utilization. We show that you can get to an 80%, 90% utilization with an N+1. That is the saving of this power. High variety of service chaining, so a lot of service chaining. Once it's easy to introduce, they generate more and more service chains. And when you have variety of service chains, the alternative of what we demonstrate, the alternative are VRails. And VRails are expensive because every time you have a new service, you have to redesign your VRails. And a VRails can, each VM can serve a specific VRail, where what we show is that the same VNF can serve multiple chaining, okay, on different subscribers, while they're not needing to include all kinds of shim and requirements. So once SFC will be deployed in all VNF type, then our life will be easier. You need to cover physical network function and support VNF without NSH headers, as I described.
Well, yeah, maybe we should go to the scale demo and continue afterwards.
Sure.
Do we have time?
Yeah,
Yeah.
You're monitoring the time.
Yeah.
Okay.
Okay. We'll just jump through the other use cases and try to see a short demo of the scale. Okay, Ariel will be my iPad guy here.
Yeah.
Good
So
luck.
what we have over here, well, Gal, yeah, have to connect to this. Or you want to explain it first?
Yeah. Okay, we have our scale setup here is constructed out of a single context node. This is a scale setup that presents the SGI LAN, the SFC use case. We have here the P gateway and the firewall. And as those of you who are familiar with the SGI LAN use case, the services are being presented between the P gateway and the firewall. So here between, we have a Tor switch with multiple computes and VMs. Some of them are the context switch. Some are VNFs. There are VNFs in our demo which are subscriber aware. And some of them are stateless. So we can do mix and match of those. Okay, you can see that in the demo, we're going to present 40 gig downstream and 10 gig upstream that runs on 1 million subscribers. Each subscriber will have approximately 2 hops, okay, in between the PGW and the router and the firewall. For that, we'll be using 3 context switch OpenFlow switches. Again, what makes them, from our view, carrier-grade switch is the fact that they can hold 100 million rules and they can handle this high rate of flow modification events.
High number of rules per second, and still 160 gigs, and very low latencies, with between 70 to 100 microseconds.
Microbes, yeah. We'll have here 4 context-aware VNFs, which is our proprietary VNFs that can do TCP optimization and header enrichment. Again, to do header enrichment, you need to be subscriber aware. Okay, you want to put inside the header of a certain packet subscriber information, or which makes you subscriber aware.
What we're doing in production, I don't know if some of them you have the services, that based on the subscriber, we put the label in the headers, and that gets to Microsoft websites. And once you buy from Microsoft, it gets deduced from your operator. So that's kind of things that you can introduce into the systems. And to have that capabilities, your VNF needs to be subscriber aware. It's not enough that the SDN is subscriber aware, the SDN that is subscriber aware, send the traffic to that VNF, specific VNF, also send him that subscriber awareness for him to function. And also for the redundant VNF that we selected for him. So the redundant VNF gets that information.
Okay. Now, to reach that traffic here in the setup, we used 40 gig NICs and SRIOV ports to get the full-blown bandwidth.
Even though some claims that the vSwitch can do high traffic, try to do that with VNF traffic. Okay? A lot of optimization in the vSwitch, in the open source, in the proprietary ones, are focusing on the data center application, not focusing on the carrier applications. They are optimizing for all kinds of 5 tuples that repeating 5 tuples. Okay? Once you have a traffic like in every second you have 1 million different 5 tuples, try to do that on a vSwitch. That optimization do not work. You need a different type of optimization in the data path in order to have that ability to run all this traffic.
Okay, I'll try to run through the demo now. So what we can see here is our GUI runs 50 gig traffic total, 40 gig downstream and 10 gig upstream. we'll also see here the distributions between, these are the 4 context-aware VNFs, okay? So we load balance in this demo between the 4 VNFs. If we'll add additional one, we'll be able to do that as well. Notice the way we do here load balancing is by load balancing each subscriber to a different VNF. Okay, that's one of the abilities when we do fine-grained rules.
While he has 15 gig of traffic in the setups, I have this iPad which connected to the setup, and I can select my own service profile into that setup as a subscribers, and I can surf the internet. So Gal can look me up into that system, and you want my IP or you want my name?
No, we'll search here, but just to see that we're around the 1 million subscribers here.
So I logged in as Ariel.
We have now 1,043,000 subscribers. We'll just search for the iPad.
Ariel. Yeah. So out of the millions of subscribers that he has in the system, he can drill into my users and see my traffic.
Yeah, and the ability of subscriber aware, one of the benefits is the ability to troubleshoot a single subscriber. I can open the Wireshark and see the traffic, I don't know, CNN or something. Okay, the HTTP traffic, I can troubleshoot, pair hop, each hop for the subscriber and see where the problem is or what is expected or unexpected in that specific point. One of the biggest challenges when deploying in telco is the ability to troubleshoot your system or troubleshoot the entire environment. We all know that the first thing that the carriers will do is try to see if the problem is the network, because that's the first thing that they can do. Okay, so once we have a system over there, we can split the problem and help the carrier to figure out where the problem is in their network by the troubleshooting capabilities.
So we've done it multiple times in production. You just take the IMSI, put it in the tool, see the traffic of that specific subscribers, and get it to the Wireshark. That's one of the most powerful capabilities that the carrier likes. Yes?
No, it's actually.
So what we're doing is having another rule. Once you click it, you have another rule that duplicate that traffic from a specific location on that chains and encapsulate it with a VXLAN to one of our VNFs that take it up to the GUI. Okay? And obviously, you can have a VNF that gets mirroring. So some of the VNFs, some of the content filtering needs just a mirror traffic of selected traffic. So all kinds of capabilities are there, but for that, it's just a...
Okay, just to see... Oh, sorry, a bit challenging. Okay, so this is the context switch itself. We can see that a single switch will be connected to all the controllers, again, for resiliency and load balancing of the rules installation. Now, what we can see here as well, it's a regular switch, okay, high power switch. We can see that in tables 2 and 22, we have approximately 2 million rules, okay? I'll try to use a different interface that most of you will be familiar with.
So we have a table for upstream and a table for downstreams. And the first table is just hitting whether, depending where you're coming from, which direction you go.
So this is the standard OpenFlow controller, okay? This is a standard interface, so we can see all the tables and the amount of rules there. We can also see the subscriber, which is 1.6. Just a second. This is the context switch, which is a high-power open-flow switch that can hold our switch. Yeah.
Yeah, we had to software.
It's a software switch. Yeah. Okay.
We had to implement because we understood that we need a lot of rules and there was any available. Just a regular Linux.
Yes. And we have here the rules themselves. So basically, it's a standard powerful open flow switch. Okay, and we'll try to go faster. We're out of time here. Also, as Ariel said, we have the context view, which is analytics view of the system. What we can see here, won't see it live. We can see here the amount of rules installation each of the two controllers had. Okay, so here we have in blue and brown, two controllers, each installed 6,000 rules a second, okay? Total of 12,000 rules a second for all three switches, okay? What we will do now is look at the GUI. We'll continue monitoring the traffic. Again, as you remember, the resiliency for telco is one of the most important things, okay? Not interfering with traffic is really important. So here we have the 50 gigabyte of traffic while we monitored this.
So we have two OpenDaylight controllers in that ConteXtNet node. We have 3 switches, OpenFlow switches, and we have 4 context-aware VNFs, okay? We'll fail each one of them one at a time and show you that the traffic is not being affected, okay? So everything is resilient.
The first thing is the VNF. Once we have, at the beginning we had 4 VNFs, now we failed out one of the VNFs.
Come to the traffic.
Yeah, most of the traffic, all the traffic that goes through the VNF should now go to a different VNF. Obviously, you see a small hiccup because there is traffic that goes through the VNF. For a short period of time, we transfer the traffic to a different VNF, okay? But from now on, at this point, the traffic continues to flow through all the rest of the 3 VNFs. We can go to the monitoring here. We'll see, maybe you remember or not, previously the traffic was around
12 gig.
12 gig each VNF. Now it's 16, 17 gig. This VNF is out.
So we had, each VNF had 250 subscribers, 250,000 subscribers on it, okay? That VNF failed, okay? That traffic in a 1 second move to the other VNFs, split with the load between them, okay? So we had to move that 250 subscribers, 80,000 goes to a different VNF. We did that in less than a second. The only way to do that is planning ahead the OpenFlow table such that you have a multiple lookup, okay? So you have a lookup to the virtual VNF instance and then to the physical VNF instance. We change the lookup of the table. The controller noticed that the VNF failed, change the lookups, and automatically the traffic split into the other VNF. Now the VNF instance, okay, suddenly gets a lot of traffic that wasn't belong for him before that. And whether that VNF is header enrichment, for example, must be subscriber aware, okay? So he needs to have that information, how to enrich the subscriber before that. So we send the information of that enrichment to the VNF that we will know that will be the backup VNF, okay? That's what telco needs.
Okay, the next failure we'll show is a switch failure. Again, we're in switch number 3. Let's summary. Just see it's an active switch. Okay, we have total of around 4.5 million rules here. Let's just shut down the switch.
We usually shut down from the Nova stop, but that's taking time, so we don't have time right now.
Again, same hiccup because traffic is being steered through the switch. Okay, those of you who saw the hiccup, traffic is being steered through the switch, and there's no way around it. We need to steer the traffic through the other two switches. Okay, but again, after a very short period of time, the traffic reaches again back to 50 gig upstream and downstream total.
What happened in the background is that for us, we can steer the traffic immediately. The controller noticed that switched down, okay? There is an open flow timeout, very short time frame. So that's a few milliseconds, okay? But that's not enough. We send traffic to a VNF. The VNF are being load balanced between the different switches. So the VNF itself needs to be aware that that switch dies and jump to the other VNF. And during that time, the controller sends a gratuitous up into the VNF saying that you are no longer being served by this switch, you are being served by a new switch. And that's how we speeded up the load between even the VNF is aware that he's now is up to another switch. Yes? Yes.
What if the backup VNF fails as well? Do you prepare all the possible configurations?
So we prepare for a hot standby on, it's depending on how much you want, okay? On regular basis is like a single failure will have immediately hot standby on second one. If the carrier wants triple failure, we can do that, okay? At some point you have to say, okay, that's how much because every time another failure is cost something, right? The VNF has to be subscriber aware and gets that load. So, but also after a certain period of time, it's configurable about time, we say, okay, that VNF dies, and you have to configure this redundant VNF. Another one, redundant for the redundant.
And come back to,
yeah.
okay. So let's continue now to the third failure we want to present here, the controller failure. Now, obviously, when you're failing out controller, it shouldn't affect traffic. You should be aware of that and make sure it doesn't affect traffic. So in controller failure, we need to look at the controlling packets, right? For example, the ARPs, ICMP traffic that reaches the controller and it handles them, or the AAA traffic. Now, for that, we'll simulate radius packets here. Okay. Yeah, it's reg on reg. It's both. We're simulating 1,000 packets per second for 200,000 subscribers. Plain radius packet with several AVPs. Sorry.
So that's simulating 1,000 subscriber attached, detached. That's what happens in usually in every carrier aggregation points, 1,000 per second or 10,000 per second, depending on the site and depending on his configuration.
Yeah, and here we see 2,000 because our management or our system here present also not only the 1,000 radiuses that the broker receives, but also the additional 1,000 radiuses we send to the context where, because it's a subscriber aware, we need to send the radiuses back to it, standard interface, and make sure it follows the subscriber awareness requirement. So, without we'll
and that
just
1,000 rules are now translating like 12,000 rules per second on the data path, right?
Yeah, well,
on the control path.
We'll see it now. Just a second. Before I fail out, we'll go to one of the switches. Actually, we can do it now. We'll go to one of the switches and see summary. Okay, we'll see the summary. And you'll be able to see the rules there.
Where's there? Just point out with the
here.
mouse, with the mouse.
Yeah, the rules in table 2 and 22 are changing in a rate of 4,000 a second, I think. Okay? We have 3 switches. 12,000 is divided to 3 switches. So now we'll fail the controller, the ODL controller. Okay? And we are still at 2,000 radiuses per second. And the controllers should be out. Yes. Okay, and the controller is out. Again, traffic should not be affected. As we go back to the traffic view, in no point the traffic should be affected. 50 gig, okay?
And my iPad, of course, also surfing through that setup.
Now, one last thing we want to present here is the restoration. The failure part is tricky and important, but the restoration part is much trickier and should be handled the same way. It shouldn't affect traffic. Okay, so at this point, we'll restore the switch, which is one of the toughest component to handle in the system. And again, bear in mind that this specific switch had 4 million rules. So the idea behind it is to synchronize the switch with all the rules and continue updating the rules in the meantime, because they are changing, the network is still live, and not steer traffic through that switch until it reached the point that it's fully synchronized and can start working in the network. Okay? So we'll just check the summary here. Again, tables 2 and 22. In a minute they'll start filling up. And in the management, we'll be able to.
So there was like a 4 million rules before that, right? If I remember
4
correctly.
million rules, yes.
Yeah, so now the controller push 4 million rules into that switch until it will be ready, functional, and only then will send traffic back to him by gratuitous ARP, and traffic will be ready and split the load between the different switches.
So the switch now is in state of recovering. Okay, you can see that the tables are being filled. None of the traffic should be forwarded through this switch at this point until it reaches its capacity. And, well, basically that's it. We won't wait till the switch is restored. It will take a couple of minutes. If you have any questions, please feel free. Yes? Yes, it's a standard interface, OpenFlow 1.3.1, I think, with OVSDB interface as well. Again, the difference between the standard OVS switch and this switch is the capacity, and both traffic, 160 gig of traffic, and the number of rules.
So basically, it will be transparent if I take this switch and put it inside.
Exactly.
Yeah, we work with Mininet, we work with the regular OpenFlow switch, that's not a problem. But to get to performance, we need our switch.
Yes. Yes.
So you talk about carrier grade, you talk about addressing scalability in HA. As you're probably aware, there's actually hundreds of requirements for carrier grade, and Telcordia spells them out quite well. One of the things I would have liked to have seen in your use cases is, for example, hitless upgrades. Right? So that's something that OpenDaylight needs to work on for Brilliant. It would be really good to see that use case because it's critical. Also, software patches. So right now we have to do a download of the entire image. No carrier would ever accept that. You really, if
Yeah, we agree with you. We definitely are in the way of that thinking. If you don't plan, there are a few things in networking and management and control. It's like if you don't make your thinking from the first day on the data path is like how you do the redundancy and multicast. On the control path is just how you do the software upgrade. That's the three major things difficult in software design on network equipment. And you have to think about it from the beginning. That's why we picked the federation model that allows us to upgrade a single controller at a time, okay, while all others are running. And that's kind of important for that. We agree with you.
For sure. One of the other things we also have to concentrate on is security. So I just have to point out, you gave me a heart attack when you're pointing out people's traffic. You know, you get arrested if you actually try to do that in a real telecom, right? You're not exempt.
So depending who's the operator and depending on who's allowed to get, of course, on the GUI, there are all kinds of permission, but yes, in production, they are using that GUI to allow them to see the traffic when there is a problem. So there are people that are allowed to see the GUI.
Not necessarily the subscriber traffic, maybe a test subscriber when you want to introduce a new service. It's very useful for these specific cases.
You wouldn't be allowed to with everybody.
Yeah, probably.
Yeah, it's not open for the open.
Yeah. Yes?
The question about your switch and how many virtual CPU does it use on this case?
So actually, the switch at the moment use like only 16 for this use case, but it can get to up to 64, depending on there are dual sockets that have like machines that have 64. On the controller, I don't know, it's like very minimal, not that many. So.
Yes? Yeah. No, you.
So my part, kind of a two-part. One is you detect the switch failure in millisecond time, so using the hello interval, the open hello interval.
Well, you have the echo first. The echoing the switch to health is one of the most important things. Also, any packet that's being received from the switch can trigger the livelihood of the switch, and it needs to be in.
Right, so if the switch goes down, then you stop receiving the echo request reply, right? So you must be at like a millisecond, like 1 millisecond or 2 millisecond rate on the message?
No, not necessarily. No, it's
So depending on the hello message, we expedite the hello message on the
it's
open flow.
I think 100 millisecond or so,
So you do 3 times low to detect,
something like that. Yes.
and you can scale that rate to 1,000 switches?
Yes, multiple connection. You need the auxiliary connection because, again, we are using here high rate of flow modification packets and packet ends, and the scale connection to the switch is fully blown. So you'll need to use multiple auxiliary connections to the switch for health and others. Okay. Yes. When switch fails, yes, you will have packet loss. From the point that the switch really failed till the through the amount of time that it takes for you to find that the switch fails, and after that you need to notify all the VNFs that uses that switch to move to a different switch and load balance it. So you will have packet loss. It is acceptable to have some amount of packet loss, and it really depends on the use case in the carrier.
But if there is a packet loss, you cannot make sure the service can be continuity, right?
You cannot.
Make sure the service continuity.
Service is so,
In SGI LAN,
Some
But-
service will be
yeah.
in some
It,
if a service fails in one packet lost, that's not a service, okay? So that's kind of I don't familiar with the service because there are always a few
Virtual
packet
information.
lost. Now, in a 40 gig of traffic, okay? So, and you have millions of subscribers on that 40 gigs, so it's not just for each service, it's a small pain, small price to pay,
Yes.
and you don't have another choice.
So for your VNF failure case, do you migrate the internal state of the VNF to other VNF?
We migrate the subscribers to use the other VNFs, yes.
What about the associated states inside the VNF?
Well, if the VNF failed, the state died. Okay, you cannot restore that state. But if you're talking about traffic state, but the subscriber state or the subscriber data is being synchronized in other VNFs as an active standby solution for the VNF failure. Okay, for fast failover.
So we try to make the VNF as much as possible aware about who will be the redundant, okay? And we have a VNF API that he communicates with us. So for cases like if it's a TCP proxy, some kind of a way, so you're not really can, TCP dies if the VNF terminates that TCP, but automatically a new one can be created on the second one. If it's more sophisticated, things like we do in the IMS is like when one PCSCF fails, even the connection is the connectionless, okay? It's like a UDP protocol. We send a message to the UE to rejoin, and we send it to another PCSCF. So there's all kinds of ways how to expedite that knowledge.
Okay, thank you.
The CPEs and Sdn Vpn, that they're somehow related, okay? So we'll demonstrate, I'll show what's in there. So I just very quickly go over these because I will have later on details. So each one, if I get it, sorry. I have the mouse. No, not this side. Okay, so this is the virtual CPE, virtual EPC use case where the data path component is actually being on an OpenFlow switch, and you have the control component, which are the regular EPC, but now they translate and move to, with the ODL controller, it moves to the context net and pushes to the OpenFlow switches. So that's on the left side. Okay. On the GI LAN, so that's service function chaining, subscriber aware, fine grain. I'll cover it later. Wi-Fi, SFC, same thing, very, very similar. And the two voice use cases, SBC load balancings and IMS load balancings, all subscriber goes to a context switch and goes to a different IMS core. Good afternoon to everyone. I know it's kind of after lunch, so we'll try to make your time. We are going to talk about carrier use cases with OpenDaylight. My name is Ariel. I'm a CTO from ConteXtream, which now it's an HP company. We've just been acquired together with me.
Gal, I'm engineering director at ConteXtream.
So as for the agenda, it's actually my first time, so I'll try to be on time and not diverted. And we have a few use cases on a large carrier scale deployment. I will just at first just introduce them. After that, we just show an OpenDaylight carrier SDN architecture, which is our architecture. What our product is based on OpenDaylight. And we will explain what it takes to make an ODL carrier grade, okay? So that's kind of a key part in our demonstration. Use cases in details after that, we will cover a little bit of those. Subscriber-aware service chaining, our key advantages in the industry is fine grain, very, very granular. We work on every subscriber, put his exact needs into the systems and configure. Now, on the business services, so you have some branch office, you have headquarter offices, and the virtual CPEs, the CPE is kind of a DOM, aggregates into the actual CPEs, just aggregate into the center, and over here it gets to an OpenFlow switch, and all the other components are virtualized inside, whether it's on the branch or whether in the central, very, very similar, and aggregates into a virtualized environment. Good question. Just give me 2 slides, I'll get to that. And business services, I'll cover it later. Let's go to your question. I just wanted to show you just what are we talking about before I drill into the architecture. So we are connecting network equipments. We are connecting a virtualized components. They are residing, whether that's in the home or in the data centers, on the aggregation points, whatever they are, okay? And they are all connected in multiple locations. And between them, there's kind of a network, whatever, layer 2, layer 3 network. We treat it as an underlying network between them. In each location, we put an OpenFlow switch, okay, which is a context switch. And together with that, we put a ConteXtNet controller, okay? Categories based on voice, consumer, and enterprise. And we do from customers categories, whether it's cable, fixed, and mobile. So we identify 6 use cases that we started to work on, and we actually in a very progress stage in each one of them. So the first 2 use cases is voice-related. Some of them we do have already in productions in a large carrier in the US. So we're doing a virtual IMS and a virtual SBC, where we take the IMS and virtualize that, make it the global load balancings between IMS cores. Same thing goes for SBC, session border controller. So you can virtualize multiple of them for NNI links. So that's kind of 2 use cases. In the consumer data, we're doing subscriber-aware service function chaining. That's for GI-LAN. GI-LAN is the endpoints of the EPC, the LTE environments, the 4G environments that you know. After that, you need all kinds of services. Most probably, most of you are getting those services, even if you're aware or not. So the ability to have all kinds of services introduced, that's kind of a use case that we do. The next use case is enabling EPC that I talked a little bit before. And the last 2 use cases are a virtual ring, OpenFlow rules accordingly for each subscriber, its own chain, and based on his requirement. After that, we will show a little bit something that's a bit more sophisticated, where we took OpenDaylight based platform, and we make it the data path of a virtual EPC. So a lot of carriers talked about VNFs and moving the component from a physical component to a virtualized component. We took that steps, but we took another steps further, is translating the data path of EPC, which is kind of a not trivial data path. We move it to an OpenFlow switch that actually performs the EPC. And the last use case that we'll demonstrate, that we'll talk about it is Sdn Vpn based on ODL, all kinds of VPN use case and virtual CPEs use case that we are working on. And at the end, we'll try to do some kind of a scale demonstration where we show a system of 40 gig download, 10 gig uploads, 1 million subscribers, and 1,000 rules per second, serving a GI LAN use case of, with a fine-grained service function chaining. So I'll start with describing some of the carrier SDN fabric that we're doing. So we split it to multiple